So today, we are going to begin trying to better understand our surface intrinsically by being able to take certain important measurements of it. And for comparison, I want to think back to our study of curves in two-dimensional space and curves in three-dimensional space, and about the fundamental importance of the curvature and the torsion, right? So remember that the curvature kappa and torsion tau were the key features of a curve in space that allowed us to completely describe that curve, right? Completely classify it up to some sort of isomorphism, right? Or up to some sort of isometry. So we want to understand the same sort of thing with surfaces. We want to try to understand what information about a surface allows us to better understand it, to best understand it, to completely characterize it. And it will turn out, though this will be a long time coming, that for surfaces in three-dimensional space, there are two objects that are of fundamental importance to us, and these are the first and second fundamental forms. It will take a long time for us to define both of these, and then for us to prove that these are really critically important to understanding the surface itself. Both quantities are challenging to compute and to interpret. So in this video, we are going to introduce the first fundamental form, and in a while, right, many videos down the road, we'll talk about the second fundamental form. Worth saying that I call these things forms. Specifically, the first fundamental form is what we call a bilinear form, while the second fundamental form is something called a quadratic form. Now, again, the second fundamental form we'll talk about in a later video, but I want to start just by talking about what is a bilinear form, or what do I mean when I use that language? Well, a bilinear form is a function, right? And it's a function, I'm calling it here function f, that takes two vectors as inputs. So it has two different inputs, and is linear in each input. So bilinear, meaning that it's linear or behaves linearly in both of the inputs. Now, what does it mean for a function to behave linearly? Well, if I have my function and it takes two vectors as inputs, right? Here's an f of v comma w as an example. Well, it's linear in the first component, or linear in the first input, if I have some sort of vector addition or scalar multiplication in that first component, and it factors in a nice linear way, the way that we might expect. So here my first component, my vector, is au plus bv, right? Here u and v are vectors, while a and b are scalars, right? So this is some linear combination of the vectors u and v. And if I plug that in as a vector in my first component, then I can distribute as I might hope. So this becomes a times f of u w plus b times f of vw, right? Where I've split up this first component, the au plus bv, in this nice linear manner. And the fact that this function is bilinear means that this happens in both components. So not only is it linear in this first component, but it is also linear in the second component, right? So if I have a vector that is broken up linearly in the second component, I can distribute and break that up appropriately. Now, you might be asking, like, what does such a function look like? This seems kind of weird. It turns out that we have one example at our fingertips immediately, right? The classic example of a bilinear form is the dot product, the good old dot product in Rn, right? And just to sort of point this out explicitly, what we're saying here is that if I were to take a dot product of two vectors, so maybe I have a w over here, and I'm taking the dot product with the vector, let's say a times u plus b times v, right? So if that's my sort of linear combination of vectors that's forming a vector over here, right? Well then, what I get is just a times the expression u dot w plus b times the expression v dot w. Right, and that, I should say that addition and scalar multiplication have been broken up in this linear way across this first vector. And of course, it behaves similarly in the second vector. Here, to be sort of crystal clear, for the dot product as our example, I'm saying that f of u comma w, if those are two vectors I'm plugging in, my function is just going to have the output of u dot w. So the dot product is sort of the quintessential bilinear form that takes two vectors as inputs and gives us this nice output computed by the dot product. Okay, now there's a really important thing to note here, which is that a bilinear form can often be represented using a matrix if we are working in a nice space like Rn, in which we have a nice basis, right? So what I mean by that is that if I have two vectors v and w, then I can compute f of vw by finding an appropriate matrix M that represents the function and then doing the computation of v transpose times M times w. So let's see an example of that, right? Because that's a little abstract. A good example of this is, again, the classic dot product. And if we look at the dot product in R2, right, the dot product can be represented using the identity matrix, the 2x2 identity matrix. And the idea here is that if I have a vector v represented in its column form as v1, v2, and a vector w represented as w1, w2, then v dot w, let me grab a color here, right? So v dot w, this is v, and I take the dot product with w, right? Well, I anticipate that answer being v1 times w1 plus v2 times w2. Right? The different sort of corresponding components are multiplied together, and then we add them all up. That's our good old friend, the dot product. Well, if I compute this multiplication, I have v1 transpose, so it's turned on its side, times this matrix times w. What I get is anything times the appropriate identity matrix is just that original vector, right? So when I multiply this together, I'm going to end up with v1, v2 times w1, w2. And by rules of matrix multiplication, this will just be v1 times w1 plus v2 times w2. Right? Of course, this is a 1x2 matrix, while this is a 2x1 matrix. So the result is a 1x1 matrix. You can think of it as just a matrix with this single entry in it. But I'll often abuse notation and just consider that number itself to be the answer. Right? So yes. So what we see here is that with our usual basis, then v dot w can be represented using this identity matrix. Now I say our usual basis by just pointing out that using this notation, the v1, v2 notation, means that my vector v is really being thought of as v1 times the vector I plus v2 times the vector j. And similarly, w1 and w2, right? This vector is just w1i plus w2j. And so I and j are my standard basis vectors in two-dimensional space. Right? But once we have explicitly identified what these basis vectors are, then I get this associated matrix. If we were using different basis vectors, we would get a different associated matrix. And I'll let those of you who have taken and enjoy linear algebra think a little bit more about that. Now, with this description of bilinear forms done, we are ready to define the first fundamental form, and we do that as follows. So let S be a regular surface, and let P be a point on S. So here's our surface, here's our point on S, with this associated tangent space that I've drawn here. Then the first fundamental form of the surface S at the point P is the restriction of R3's dot product to the tangent plane TPS. And we will denote this by using sort of this Roman numeral 1, kind of looks like an I, but Roman numeral 1 sub P. And so this is our function, this is our bilinear form, and the way that I compute it is if I have two vectors, A and B, and these are vectors in the tangent space at P, so maybe this is my vector A, right? And maybe this one right here is my vector B, and they are living in this tangent plane, then the first fundamental form of A and B is just equal to A dot B in the R3 sense. Now, worth pointing out, or being sort of completely precise about this, worth pointing out that these vectors, A and B, these are vectors in TPS, right? These are vectors in that tangent space, while when I compute this dot product, I'm computing this as if they are vectors in R3. And of course, we can do this because TPS can be thought of, these are vectors in R3. Right? And we can do this because our tangent plane is just seen to be sort of sitting here in three-dimensional space. So any vector that's drawn in the plane is automatically also a vector that's drawn in 3 space. And so we can just think of it as being the corresponding vector in 3 space when we compute that dot product. Now, it's worth explicitly pointing out, and I'll remind you of this again down the road, but every single point P has its own unique tangent plane associated with it. Right? If I had chosen a different point P, I'd be looking at a different tangent plane here. And therefore, every point P has a different first fundamental form, right? A different first fundamental form at P. Right? So if we're looking at a different point P, we have a slightly different tangent plane and therefore a slightly different first fundamental form. All right, love it. So that being said, we can now ask, what is the associated matrix that corresponds to the first fundamental form? This matrix will be helpful when it comes time to do computations involving the first fundamental form. Well, we've claimed that we can find an associated matrix once we choose a basis of our sort of vector space that we're looking in. Right? When I was trying to do the dot product in R2, it made sense to use the vectors I and j. If I'm trying to look at the dot product of vectors in R3, it might make sense to use I, j, and k. But actually, in this case, the fact that we are looking just in a subset of R3, right, just in the tangent plane, means that I only really need 2 vectors to describe it, and there are actually 2 very natural vectors to choose. If we have a parameterization of our surface, so if our surface is defined using a parameterization, fix that there. If it's defined using a parameterization, right, a capital X, then a natural basis to choose is going to be the basis that corresponds to the vectors x sub u and x sub v at a given point. All right, and here's what I mean by that. As a reminder, if I have my my parameterization, right, is going from some set u onto my coordinate patch over here, right, onto my surface S, and every point over here corresponds to a point over here. And so if I'm looking at the point P, let's say, I can really think about looking not at this point P, but at the point mapping to P. I can look back at this point in my domain space, and the natural vectors over here, right, the vector that corresponds to one vector or one unit in the pure u direction, and one vector here in the pure v direction, will correspond to these 2 vectors over here in this space, right? So my vector in the u direction corresponded exactly to the vector x sub u over here, right? So that was the u derivative of the parameterization. And my vector pointing straight up in this v direction, that corresponded to x sub v. Maybe going down here in this direction. And so these 2 vectors might not be orthogonal to each other. They might not be pointing 90-degree perpendicular angles away from each other, right? They might not even be the same length. They might sort of be different lengths, sort of tilted and you know, with a small angle between them. But they're definitely pointing in 2 different directions if our surface is regular, and they are definitely both pointing within the tangent plane. They are tangent vectors. So as a result, my tangent plane, right, and maybe here my tangent plane sort of looks like this, right? My tangent plane to the surface at this point can be nicely described by using these 2 vectors, x sub u and x sub v, as a basis. And all I mean by that is that any vector in this space over here can be described as a linear combination of x sub u and x sub v. Now, with that being said, I'll just scroll down this far, right? If I take a vector A or a vector B from this tangent plane, I can write it as a linear combination of x sub u and x sub v. So maybe specifically, right, if I have a vector, I don't want this picture to get too messy, but if I have a vector, let's call it A, but let's say that it's the vector that goes 1 unit in this direction and 1 unit in this direction. That's like this vector right here. Right? Well, that will be the vector in the tangent plane that goes 1 unit in the x sub u direction and 1 unit in the x sub v direction. So that's going to be pointing sort of in this direction, but still fully within this tangent plane. Right? And so similarly, I can describe any point in this tangent plane as a linear combination of x sub u and x sub v. Now, if I am choosing to do that, so I'll write my vectors a and b as a linear combination of xu and xv. So a is written like this, b is written like this. I can then represent these in a column vector form, right, as a1, a2, and b1, b2, with the understanding that a1, a2 doesn't mean a1i plus a2j. It means a1 x sub u plus a2 x sub v. But given all of that, if I represent my vector in this manner, and I represent my vector b in this manner, then let's see what their dot product is, right? So the dot product, the first fundamental form of a and b, would just be the dot product of this linear expression dotted with this linear expression. And by our rules of bilinearity, we can basically distribute this, right, and fully expand it to get this expression down here. We end up with 4 terms, right? A1, B1, and then it's XU dotted with XU. And then similarly, there's an A1, B2, XU dotted with XV, an A2, B1, XV dotted with XU, and an A2, B2, XV dotted with XV. So we fully expand this, we get these 4 terms. And this can be represented very nicely in terms of our vectors a and b. Specifically, we can represent it using this matrix right here. I'll sort of frame that nicely there, right? So if you want to pause the video and just sort of check that, you'll see that computing this expression gives you exactly this multiplication up here. And so this is a nice matrix that represents our first fundamental form. Now, we can conclude, right, or we can conclude that with the following statement, right? The first fundamental form is classically written as a matrix, and typically the language that we use, it varies from source to source, but you either use the letter G to represent the first fundamental form, and it's G11, G12, G21, G22, or you represent it using the capital letters E, F, F, and G, right? Where these entries, the G, I, J's, or the capital letters E, F, and G, are all coming from this matrix right here, right? So in particular, the G11 entry, that upper left entry, is just x sub u dotted with x sub u. The G12 entry is xu dotted with xv. Of course, because the dot product is also symmetric, the G12 entry is the same as the G21 entry, right? That's why the F's are both the same. And finally, the final entry, the G22, or if you want the capital G, can be just the dot product of x sub v dotted with x sub v. So once we have a parameterization, once we have our capital X, we can compute x sub u, we can compute x sub v, and then by computing these dot products, we can compute the entries of our matrix representation of our first fundamental form. And so next video, we will see how we can use these to aid us in computations.